Okay, great. We're going to start with something very elementary. So this is our first exercise. Is this showing up? What's wrong? Okay. So our exercise is this. V is n-gon in R2. So it has n sides. V contains a unit disk. Okay. What's the lower bound for the area of V? What's that? What's a better lower bound? So I want show A of V is bigger than or equal to what we're going to call A of N, which is the area of the regular n-gon that has inscribes the unit circle. So pi over n, and this is, or say this is the regular n-gon with radius 1. Now, this is an exercise, so I'm leaving it to you. It's really not. No. Yes. This is.
I want to see the solution.
I don't have that ready. No, it's okay. So I will get you started, and then it just comes down to. First of all, is it clear that if we have a general n-gon, say 4-gon, that we can shrink it so that every side touches the circle.
Yes, sir.
So we can always, however you want to do that. And so there's another n-gon that has smaller area that contains a circle. And then we can look at the points. I've got one more here. I think I've got one more to go. We look at the points of intersection on the circle, and then you can bound. Then it becomes a Jensen inequality, a convexity argument. Okay, so that's all I'm going to do. That's the exercise to finish that, and we'll need this. Oh, the other thing that's we could do, I'm not going to. It's easy to take the first and second derivative with respect to n.
So this is n times the tangent. It's not some kind of
n times the tangent of pi over n. That is the area of the regular n-gon within radius 1. A, the smallest n we'd be interested in is 3. A defined on 0, 3 to infinity. Well, to whatever, is decreasing. So the area decreases as you increase the number of sides. Decreasing. And convex. So A, here is 3, 4, 6, We are really only care about A is defined for any value of n, say bigger, but we only care about it on the integers. Okay, convex and decreasing. So we're going to use the convexity of A in the following argument. So this is the theorem of Fayes-Toth that will imply that the hexagonal lattice is the best packing in R2. Theorem, at least in this form, as far as we know, it's Fayes-Toth. Okay. So now suppose omega is a convex polygon. This will be our large guy with 6 or fewer sides. So it's a nugon with new 6 or less. The 6 is only a convenience. In our estimate, if we have more sides, the number of sides comes in. This makes the estimate a little easier. We have n disjoint open balls or open disks. X, I, R, all of the same radius. I equals 1 to n, n, v. So we have a pack or an arrangement of n disjoint disks in, omega. I need to look at my notes here. So let me draw a picture. So omega is whatever large set you like. This is omega. And then we have n non-overlapping open disks in omega. Then the consequence is n is less than or equal to the area of omega divided by the area of the hexagon within radius r. Okay. So you can rewrite that as the area covered by so the area covered by these disks, n pi r squared divided by a omega. That would be the fraction of the area covered by your packing divided by the area of the large set. Then you rewrite this. It's you bring what? I bring the r up, r squared here, multiply both sides by pi, divide by a omega, and we get pi over a of 6. And you can check with the tangent of pi over 6 that this is pi over root 12. And so this gives the packing density. So by picking an arbitrarily large polygon, this says that the largest we can cover is this. One of the reasons I like this proof is that there are some quantitative estimates.
That's the theorem, it's not a proof, right?
What? This is a theorem.
Yes, you haven't proven it yet.
I haven't proven it yet. So we're going to go through this. Okay. But as a consequence, the proof contains some elements that might be useful if you're wanting to estimate, if you're at a high density, if you're close to this density, there are some explicit estimates that say, okay, how many non-6s can you have? How many regions of the 6s, which ones, how many can be not close to having the area of, okay, so that's what our goal is. Okay, so let me try to figure out, put that right there, I guess. That right there. Okay, so I'm moving slowly, sorry. Okay, proof. This, I hope to get it all on this. Okay, so now I'm going to let omega, let me pick it to be a square. And let me make n not very large, so my picture works okay. So say like this. Okay, May 05, I did 4 in my notes. Let me see. So we have non-overlapping. I hope I did I do this okay? Well, okay, these are all supposed to say same R. It looks like they all, okay. Then, so we have B, XI, R. These are in omega disjoint. Now we do the Voronoi tessellation with respect of omega with respect to the points, the centers. So this collection VI, I equals 1 to n, is the Voronoi tessellation of omega with respect to our centers. So let me see if I can draw that. Boom. 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 I don't know, all these bisectors, I'm probably going to mess it up, something like that. Okay, maybe that's it. Okay. Is that close enough? Okay. Do I have everything I need? I hope so. Okay. I am going to skip a couple of things like we did. No, where I'm sorry. So the one thing I'm going to skip, but this is exercise 2. Exercise 2. Exercise 2. Yeah, this exactly. Exercise 2 is that Euler's form. Well, the Euler's formula for planar graphs. When it's a simple calculation, but when we have 6 or fewer sides, then we get that the number. I'm sorry, I forgot. Each VI is a new I gone. So new I is the number of sides of the ith Voronoi. So VI is a new I gone. Yes.
I see you coming.
Okay, great. Excellent. So what we know from the Euler's formula that you can write it a couple of ways. I'm going to write it as the average new. So I'm going to call this new bar is going to be 1 over n. I equals 1 to n. And the result is that is bigger than or equal to 6. If you had more sides, there's going to be something about the number of sides divided by n in this formula. So it's not a big deal. Okay, but the restricting to 6 or fewer sides of omega when you do the Euler formula kind of gives us this nice exactly 6 without any other term. Okay, so this is kind of adding up the edges, faces, vertices, and okay, great. Here we go. Here's the proof. A of omega is going to be the sum of the areas of the Voronoi cell, the tessellation. Okay. Now, VI is a new igon. So if I replace each of these, a new igon with n radius r. So this is going to be r squared a of new I. That's just scaled the first exercise. Okay. And then this is, so I'm going to, I always have to set up Jensen, kind of make sure I get it. I'm going to pull out an NR squared. I equals 1 to n, A of nu I, and then I have my probability measure 1 over n. Okay. And then this is bigger than or equal to NR squared. So here is convexity. A of I equals 1 to n. I needed a 1 over, no, yeah. Yeah, 1 over n nu I. So we take the average of the values of the function is bigger than or equal to the function applied to the average. And so that is NR squared A of nu bar. Now nu bar is, let me get this, bigger than or equal to 6. A is decreasing. So this is bigger than or equal to NR squared A of 6. And that is equivalent to this. Okay, there are a couple of steps in here. So where was my graph of, here, I'm going to pull this up. Yeah, so by looking at the small gap between A of 6 and the linear interpolant, you can estimate you can get a bound on the number of non-6 guys in terms of how close you are to the bound. Yes. You can also get bounds here on if A of how many Voronoi cells can have significant excess area. Okay, so anyway, I'll stop with that and then let me go on to the, yeah, well, that took a little longer than I thought, but it's okay. So yeah, if you can help me get to the slides. So now the advantage is now I can click through my slides quickly since I'm rushing. No, no, I'll try to. Whatever we get to, we get to. No, I want to just use the. Okay, so I want to, this part is, Alex may say a little more. I wanted to quickly mention a couple of refinements of the type of energy problems that we consider. And then I'm going to talk about periodic problems. And one of the reasons I want to mention this is we can use some of these modifications to prove things in the periodic case. So just quickly, there are two types of, especially when we're interested in generating non-uniform distributions, and say someone gives us one of the businesses where we try to be in is in kind of the discrete, approximation community who wants good point sets for numerical algorithms or visualization or whatever. So you've got some target distribution on some region, and you want to come up with kind of optimization problem that in the limit of large number of points, you generate this. And also because of the repulsion that we build in, they have nice separation properties. We can prove also nice covering properties. They generate what is called quasi-uniform sequences of points. So anyway, first of all, if we add a multiplicative weight, so then what we really need is that when xi and xj are close, we need continuity and positivity to preserve kind of the repelling nature of this. And then it's not too hard when S is bigger than B, when we're in this short range case, to establish that we get points. I'll show some pictures in a second that are distributed with this density rho. If we, for example, pick W in this way. More generally, you give us a W, we tell you what the distribution. If you give us a rho, this would be one way to get that density. I'm going to need this when I get to the periodic case. That's the main reason I wanted to mention it. We can also add an external field to these problems. Then here is actually the formula. So W needs to be this CPD weight. In particular, on the diagonal, you want it to not be 0. You have an external field for these problems. For this to kind of have a limit, we need to weight this external field by n to the s over d. And then in the limit, you've got a formula for, okay, this L1 is a little annoying. It's kind of like filling a bathtub up. You have to pick this constant so that this thing is a probability measure. Okay, so, okay, maybe Alex. We also do this with really short range by restricting to the k nearest neighbors sums. It's interesting, then it takes the long range, what we think of as the long range, where S is less than B. When you restrict just to the k nearest neighbors, you get a short range problem. And this density result holds all the way down to 0. Okay, I think, let's see, do we have one? Okay, here's the kind of thing. So this is, I don't know, it's not the, hard to see. This is showing the Voronoi tessellation, the points we should have made a little larger. You can see a few of them. And this is on some kind of algebraic surface. Let's see, Alex chose to make the density proportional to the third variable squared, just for an illustration, not for good reason. In applications, you might want a density that's larger where you have more curvature, or, so these are. But this is what I really want to talk about, because this is closer to what Danilo's been talking about. And there's some, yeah. So we've already talked a little bit about CS, this constant. In some cases, the constant that reflects the local structure in dimension D. That local structure is a lattice. And so we've already encountered lattices a little bit, right? So Rivet lattice for us is the integer linear combination of the collection of the basis in RD. Now, if you interchange the order in this periodic problem, then you can set up a periodic potential that I'll draw a picture in just a second what we're doing. I mean, so as long as you have sufficient decay and if your initial pair interaction is given by small f, and then you sum over all of the x plus all of its lambda translates, then that's what we'll call the periodic potential. So you can think of it as the energy required to place a unit charge at x in the presence of all the charges y plus lambda. It's immediately lambda periodic. It kind of does it when you do minimum energy problems. You can pick a fundamental, you can always assume that your endpoints are in a fundamental domain or not. Okay, so we're always kind of working mod the lattice. We last time discussed what we call the, I think we did this, right? So we would call this an Epstein Herwitz Zeta function. I don't know what's the right term. So it's the lattice. What it really is the potential energy no, this is our full energy. Okay. But let me just click the next slide because there we go. So we have x and y, and then if this is y, these are the translates of y, and so this is the energy associated with x and all of the translates of y. And this will converge in dimension d when s is larger than d. When s is equal to d, it's like a harmonic sum. And when s is less than d, you have to do something else. So first of all, this zeta function, these zeta functions, when x minus y approaches points in the lattice. So for example, when x minus y gets small, then this is dominated by the Riesz potential. And so these, you can incorporate a W of xi, xj, and it follows from our weighted energy problem that in fact, for the hypersingular case, for s bigger than d, that we can use our previous results to prove that the CSD that we associated with just the unweighted problem is the same, and that I guess I didn't write this, that optimal configurations are uniformly distributed on the fundamental domain. Now, these are theta functions as well. So if you periodize the Gaussian, so this is for me how theta functions, these arise. These are going to be Jacobi theta functions of, I think it's type 3. Okay. This is an example of we're summing these Gaussians depending on the parameter A. This is the type of interaction that we're interested in. We're interested now in finite n periodic, lambda periodic problems. And we'll say that if a configuration is optimal for all of the theta functions for all the parameters A, then it's an endpoint lambda or it's lambda periodic endpoint universally optimal configuration. Okay. So this is more specialized than the arbitrary Euclidean space ones. Okay. So it could be, yeah. Before we go further though, I probably should have rearranged these. When you have long range potentials, for example, for S less than D, at less than or equal to D, there are a variety of ways, and many of the people in this room know more about all the different ways to subtract off the infinity that's coming from the non-convergence of these series. And so the way we like to do it, and we're not original, but it's often done in physics this way, is using convergence factors. And so what's interesting, so the zeta function is an analytic function. And so it's an analytic function of this parameter S. And so for S larger than D, we know its values. It has an analytic extension, which is kind of a mathematical concept of, okay. And so you'd say, well, why does that? So what we're going to find out is that the analytic extension is usually also the object that appears when you do, say, convergence factors or jellium or other type ways of subtracting off the long range behavior, the long range divergence. Okay, so anyway, what we do is, so for example, I'm writing this now using the Gaussians as the convergence family, but really what you need for a convergence family is that, first of all, for whatever family of potentials you're trying to, or long range, and you're trying to work with, you need that this product, these convergence factors, have sufficient decay so that you can just plug them into the sum and add them up. Okay, so you accelerate the decay. You could have a window function that truncates. Okay, you want sufficient decay so that you can form these sums, and then it's a family, and so you want that as this parameter, typically you use 0. Certainly this would be work for the Gaussians. As this parameter approaches a limit, the convergence factor goes to 1 for all x. So it's going flat. So point-wise, this thing as a goes to 0 is approaching this. So this is the machinery of convergence factors. We need those two properties. And then we're interested in under what conditions. And so we have there's a bit under assumptions about this guy. So right here, I'm doing it for Reese, but you can do this for other things. Under assumptions on this family, on this potential, you can show that under certain assumptions, which Reese satisfies, that you can write this subtracting off a constant. This is essentially looking at the 0 frequency behavior and subtracting off the 0 frequency from this periodic problem. But what it says then is that when you are interested in how does the energy vary, this constant you subtract off doesn't depend on the configuration. So if you're just interested in how the energy changes when you change the configuration, then this constant CA doesn't matter. So you're kind of approximating it by things. Anyway, this will go to infinity. So but that's how we like to. And this There are other ways of truncating, but this seems to work the best for us. Then with this, we're able to talk a little bit, and I will mention some other results down here, although that the second order term for the periodic energy, so this is, when you take the lattice, got it written with covolume 1. This is the term we talked about last time. This is going to be the term coming from the integrable kernel part, the n squared term. This is the next order term that's going to be related to the local structure. For example, in 2 dimensions, this should be the conjecture is that this would be the zeta function for the equilateral lattice, although it's this analytic extension. But it's the thing that comes out of the convergence factor, plus, so that whatever else is smaller. And then, okay, for log, this is the term that's coming in from the this is the term that's coming in for the n term. Close to the time we're trying to do these, so Marcia and Sylvia have very nice results about this that goes down to d-2. It's more general. It's got in their paper they show that this periodic is equivalent to some other ways of thinking about the second order term. And I may not, in talking to Codina, I'm not sure, so I may have confused this with the optimal transport paper, but there's also, anyway, they also have very nice work on second order term for these long range potentials, where the second order term reflects the local structure. Lauritsen has a very nice review on a number of these different notions of how to consider long range, how to get some type of renormalized energy. I'm going to skip this. Oh well, okay. I mean, we've heard so. We've talked about universal optimality and the various conjectures. And that optimality for the Gaussians implies universal optimality. Okay, I now want to talk about some fixed n problems for small cardinalities, and we're slowly making progress on low cardinalities. So if you have more questions about this, definitely talk to Nate Tenbass, who's here. Okay. So I just want to kind of make it clear what we're doing. So if the hexagonal lattice is universally optimal, then a consequence of that, universally optimal in R2 in this general sense over all range point configurations that have some fixed density. Okay, then in particular that applies to periodic configurations, and so it implies that so it's a weaker property that periodic configurations will need to be optimal under amongst all other periodic configurations. Now, if you can take the number of points to infinity, or the size as then that's enough to recover the full Euclidean one. Okay, the full Euclidean universal optimality. So anyway, the universal optimality for lambda 2 implies that if I take, say, the hexagonal lattice and then pick a sublattice, then the points in the lattice kind of restricted to that fundamental domain will be a lambda periodic, will be an optimal configuration. It will need to be a universally optimal configuration. So here we scale the sublattice as you scale by 2. One choice of 4 generators are these. And so if the full conjecture is true, then amongst all periodic configurations generated by 4 points, periodized by the sublattice, then a configuration like these 4 points or something isometric to them will have to be optimal, universally optimal for all Gaussians, for all theta functions, I should say, because now our interaction is this theta function interaction. Okay, so that's 4. Well, it turns out, so Nate has worked hard. We got 4. Okay, 9, we don't have 9. Here's something, it's just these problems are really cool. So here is a optimal, it's not going to be universally optimal, but it's optimal for a particular value of A. I think the way I had things normalized, this is A not too big. So I'm looking, but if you did Reese for some range, we would get something like this. So this is a cool kind of optimal as far as numerically optimal, that no proof for that, okay? But it's a cool one. When A is like 100, this is almost the best packing problem with the Gaussian potential. When A gets big, it's dominated by the nearest neighbor. Yeah, go ahead, Richard.
So you found it numerically.
You found it numerically. We have not proved anything about these. I'm just showing pictures.
But in theory, is there a way that using the computer kind of certify that nothing else can be going on?
So the method we're using LP bands that are set up, that are adapted for periodic problems. And if you want to ask Nate about what we're doing, I'm not going to discuss that.
But like, without the proof,
so for like 4, so we've got very low. So we've got I'll show 2, 3, 4, and 6. 4 and 6 are the new ones.
So this is not 100% certain.
No. I don't know. It's just a cool picture, and I love to. It feels like they're depending on the lattice you use. Oleg Musin has a nice paper about packings with periodic packings for Z2, and there they use the contact graph kind of stuff to establish some optimal packings. But no, it's not going to work like this. Yeah. So okay. So Eugen Su, who's really good PhD student and then disappeared. I don't know where he is. If anybody knows Eugen, tell him to contact me. He tried to talk to his old friends. They don't know where he is, somewhere back in China. Anyway. For 3, so if you rotate the A2 lattice by pi over 6, and I think pi over 6, and scale by √3, or you take the sublattice generated by these 2 points, then you get a 3 periodic configuration. So you can move these guys anywhere, and you only increase the energy. Okay, and this must be known by other people, but it was a non-trivial proof as far as we can tell. It's interesting that because of the symmetry here, if you remove a point, then that's the optimal for 2 points. So this kind of honeycomb structure is, but it's kind of like, okay, with the symmetry, these 2 points are identical when you look at a fundamental domain for the G2 symmetry. Okay, so maybe it's not so surprising. So Eugen showed 2 and 3, and these are unpublished because he disappeared and I couldn't figure out, didn't seem like enough for a paper. Here are the 4. Okay, so we already talked about the 4. We're picking this sublattice. If you pick this rectangular sublattice, it in some ways simplifies the linear programming bounds where the class of polynomials, the things that generalize, that are kind of the notion of Gegenbauer polynomials that are used on the sphere that we use are simpler in this kind of thing. Of course, if we could take either one of these and then take a family that scale those by scale up, then that would be sufficient for the full lambda 2 universal optimality, but we're probably a little bit away from, and probably other methods will come before we finish that, but who knows? Okay. I'm just about out of time. Anyway, if you want it, the 6, this is a cool one. So you take these as generators, these as generators, amongst all possible 6-point configurations that are periodized with this rectangular lattice. This is the optimum. Yes.
Just something comes to mind. So in general, if nothing forbids that you could have another lattice that is not a sublattice of this lambda 2.
That has a lower 6 point. So for us, when we
other universal optimal respect to this lattice configurations.
Right. So we're not varying the lattice and showing that amongst all 6-point periodic configuration. But to establish universality, we don't need that. What we need is to be able to do this for a sequence of problems where the cardinality is going to be.
So it would be nice to find an exotic lattice where you don't get you still get the universal optimality.
Yeah, it does seem like there will be some cool cardinalities and lattices that just fit together that might then make it almost trivial to prove optimality using linear programming.
Or any contour, just take the minimum of the Gaussian and hope that it stays in the same point.
Yeah. I may fill this in. I did want to advertise that in Eugen's thesis, there's a nice proof. That's what of the one-dimensional universality that that is based on mapping. You take an endpoint periodic, a Z periodic configuration, okay? And you want to show that equally spaced points are optimal for all of the one-dimensional theta functions. That would be equivalent to the Z universality. You can do this for all n, or at least a sequence of n going to infinity, but you can do it for all n. And what you do is you take the theta function that's giving you the interaction on the line, and you replace this, you do a change of variable to this is one periodic object, you change to this, and it turns into the problem of endpoints on the circle. And what you need to know is that this function is what's called absolutely monotone. So as a function of this variable. Okay, and the fact that it's absolutely monotone then you can use the universal optimality of equally spaced points on the circle to then map back to the universal optimality on the line. So really, and to prove, this must be known, I don't know, but to prove that the Zeta function is absolutely monotone, which means all the derivatives with respect to this variable are non-negative, you can use the triple product formula and for this theta function, and that will show that all these derivatives are positive. And so this is really, and and we did mention this to Henry Cohn a number of years ago, and he said that, oh yeah, they had discovered that as well, but that was after they'd written the proof that they had. And so I think this is the simplest proof that I know of for the universal optimality. Okay, I'm going to stop here. That's it.
Any questions?
Yes.
It's a really nice proof you showed us of the Bayes top theorem. What goes wrong in 3 dimensions or higher?
So I don't know that it goes. I don't know. Go ahead, Merchant. I haven't thought about it.
Oleg was asking this question on 3D of the best tangents that you can find. Was there at the conference in Brown in 2018? He was asking this question. And bro, I don't remember if he was asking it or he resolved it. How do we place tangent planes and tangent planes on S2 so that you get the smallest volume? This is a difficult question.
And that's how you get your enumeration. I mean, that's how you get your get onto the computer, right?
Yeah. I don't know. Right. I don't. So, and also in 3 dimensions, I think there's things don't tile like hexagons do, right? These Voronoi, they're not, the Voronoi cells are not going to be.
It's just interesting to have an analog of this
Okay, I don't have a good answer.
You know,
That's my.
not for all n there is a regular polygon of n faces. Right. So that's a difficult question for the n that you don't have platonic solids.
Right.
Yeah.
And that they don't tile is the next harder question.
Yeah.
So, but Oleg Music had this open question in 2018. I don't know if they solved it. I guess not.
Okay.
A short break while we set up yellow and then